we are not going to get any degradation or the loss as time changes. So this is also one of the property of this one. Now, what is the history when this particular magnetostrictive transducer has been generated? So its history has been began long ago in 1840s. So James Prescott Joule in 1880 to 1889 positively identified or searched the change in the length of ion sample as its magnetization changes. As its magnetization changes. I have given you example. Now, suppose this is the one table. On this particular table, I am having a small pins. These are nothing but the pins. Okay. Now, here, suppose I am having a magnetic field, or not a magnetic field, but a magnet. So, depending upon the variation, no doubt this particular magnetic fields are going to attach to this one. So, its length is going to change because at one moment either it is vertical, either it is horizontal, either it is vertical or horizontal. Now, when you are trying to bring that particular this one magnet near to the pins, its length is going to change. Its length is going to change. Okay. So this is also having a inverse effect, and this particular inverse effect is also specified as Worley's effect. So inverse Weidmann's effect, also known as Worley's effect, is the next one. That is the inverse only. As Magneto effect is used for magnetoelastic torque sensor. Oh, so this can be used for the torque measurement. Torque measurement is opposing force. Opposing force. So Lee in 1955 and Larchuris in 1943 has introduced that particular aspect. So what is this concept of magnetostrictive transducer, or what is this effect? Actually, this effect is called as a Joule's effect. Why this is so? Because Joule is the scientist who has discovered this particular effect. And the most common way of magnetostrictive approach is it utilize or it has been used in the magnetostrictive actuator. So a transverse change in the dimension, that is nothing but the length, accomplish the length change produced by the Joule's effect. Actually, whatever the change due to that magnetic field which is arises, it is totally due to the this Joule's effect. That transverse effect which is carrying out, it is totally depend upon the Joule's effect. So the reciprocal effect in which applying a trace, now there was a strain, that means the length has been changed. But if you are applying a trace or a compression or elongation to the material, that may also lead in the change in a magnetization field also of the magnetostrictive transducer. And this effect, actually reverse effect, in one of the case what is happening, length is changing. In one of the case, depending on the length, your magnetic field is changing. And the change in the magnetic field is called as a Worley's effect. And this is opposite to that of Joule's effect. This is opposite to that of Joule's effect. So this is also referred as magnetostrictive effect and magnetomechanical effect. So your Joule's effect is magnetostrictive effect and your Worley's effect is magnetomechanical effect. So Worley's effects are commonly used in magnetostrictive sensors or transducers. Now, actually what happens with that particular aspect? So here the presence of both direct and reciprocal Joule and Weidmann effect, the presence of both direct and reciprocal, that is magnetostrictive and magnetostrictive that is Joule's and Verlis reciprocal of the Joule's and Weidmann's effect leads to the two mode. There are two mode of operation for magnetostrictive transducer, and what are they? One is your mechanically energy has been utilized to convert into magnetic energy. Mechanically energy is used to convert it into magnetic energy, and vice versa of that. So first one is magnetic energy to the mechanical energy, means that energy has been transferred, transferring magnetic energy to the mechanical. And in second case, that is Verlis effect, your mechanical energy is converted into your magnetic. First one is the Joule's, second one is the Verlis effect. So in the first mode, what practical application that we people can execute using your Joule's effect, that you can design a actuator that will try to produce a motion or a force, that will try to generate a motion or a force, and in the design of that particular sensors for detecting magnetic field state. How this is so? Suppose we are having one of the sensor or a switch that is activated. That is activated. You people may have studied the concept in your control system components, operation of switch, uh, non-contact type switch, contact type of switch. In that one, if you try to recall the working of the switches, at that time you will try to gain the basic concept that this actuator that is going to generate either motion or a force depending upon the design of the sensor for detecting magnetic field, means it may, when you are trying to bring a magnetic field near to the sensor, so either it will try to actuate, it will be the circuit will be open or circuit will close depending upon its operation, whether it is normally open or whether it is normally closed. If it is normally open and if you are bringing that magnetic field nearby it, then it is going to become closed. If it is closed, then it is going to become open. Okay. And in the second mode, it's designed used in a design of a sensor for detecting the motion or a force. This is used for detection of a motion or a force. So in a design of a passive damping device, this despises a mechanical energy. Now here your second aspect, that mechanical energy to magnetic energy as magnetically and or electrically induced thermal losses, and the design of the device for inducing the change in the material magnetic field or magnetic state. Okay, so what are the characteristics? I have already specified the characteristics, that this is means converting the magnetic energy into mechanical energy uh, due to the magnetostrictive material. Okay, and vice versa of this one. Either magnetic energy to mechanical or mechanical energy to magnetic. Mechanical energy to the magnetic. Okay, uh, if your magnetostrictive material is magnetized, it strains, it strains, or conversely, if a external force produce a strain in a magnetostrictive material due to the continuous attachment of any material, this actually happens. So strain in a magnetostrictive material, the magnetic state of the material will change. Okay, so your magnetostriction, as it is having the inert property that doesn't changes or that doesn't degrades with a time. This is very significant characteristics of that particular magnetostriction. So another one is your principal operation of this transducer depends on the change of permeability of the ferromagnetic material, because we people are, for the magnetic field we are using the ferromagnetic field, and that ferromagnetic fields are nothing but it is the nickel, yeah, so when they are subjected to the strain. So this is the concept. If you try to observe this particular aspect, here is nothing but this is your that particular mean where you people are magnetostrictive material or the probe. Here we people are applying a force. This is nothing but the coil. And as you people have already seen, if there is a motion in LVDT, actually if your motion is there, its magnetic flux is going to change. In the similar manner, depending upon the force that has been applied on your probe or magnetostrictive material, the output generated across your magnetic coil due to the motion generated by the force that has been applied, it will try to generate the output. So that can be calibrated in terms of your force. So at the right hand side, an actual magnetostrictive transducer for your ready reference has been shown. So magnetostrictive transducers are likewise. So actual magnetostrictive transducer, image of actual magnetostrictive transducer is shown for you. Okay. So this is the case study. Uh, Very interesting part. If you try to observe, now we are moving in the this direction also. We are moving in the this particular